So this is how NASA reinvented the wireless
This
system.
metal is about as close to magic as it is possible to find in nature. I just don't get it. It can
Making a
adjust
spring or
its
something.
arrangement of atoms to return to some predefined shape. But it also converts between mechanical and thermal energy, and it can stretch up to 30 times more than an ordinary metal and still spring back to
Intensifier.
its original size.
I can feel it in my hands shrinking back.
Because of these unique properties, it's being used in everything from medical devices to toys to bulletproof bike tires.
Yeah, okay.
And it's allowing NASA
That's nice.
to reinvent the wheel for space exploration.
This is the bones of the tire.
The bones of the tire is a slinky.
So basically, this is the slinky applied to the rim.
Yeah,
Just
bulletproof.
wrapped a slinky around a rim.
Yeah, it
Wire.
doesn't get any simpler than that, right? Here is a bicycle that has slinkies inside a polymer. If you look inside there,
This tire does not require air pressure to work. The structure and shock absorption are all provided by that metal slinky.
So that's like around 100 psi, or what a normal road bike would.
A metal
Which
slinky.
means you should be able to puncture it with no loss of performance. So we're gonna drive it over a bed of nails. But first, we'll test a traditional pneumatic tire, just to make sure these nails are sharp.
It's definitely popping.
another puncture, another flat tire.
This one kind of expected. So now I'm going to put these airless tires to the test, driving over the same
Here we go.
bed of nails.
Should make the popping sound, but
I heard a lot of pops. I must have hit some nails. I don't feel anything different. Still
it
rides
still
well.
stays the
Pick up
same.
some speed.
That's definitely a nail.
Like the nail broke in it? Why is it?
That's what it looks like.
Yeah, the nail's in the tire.
We're now going to try to shoot a bullet into the tire and see what happens.
3, 2,
Yeah, it's firing blindly.
There it is.
there it is.
It just goes in again.
Wow. It's a really clean shot straight through.
Yep. Barely even see the mark on the tire. Looks like this one actually hit the.
Alloy?
Yep, it does to me.
Yeah, that's what it feels like.
You can see we spliced off some of the bullet before we even got to the cardboard.
How's it ride?
Yeah, no problems. Bulletproof bicycle.
This bulletproof bike tire actually comes out of NASA's research into making wheels for space missions. It is really hard to make good wheels for other planets. I mean, a lot of the places we want to send rovers to, there is no or very low atmospheric pressure.
We can't use rubber pneumatic tires because of the extreme conditions on the Moon and Mars. There's no confining pressure outside of it. It could basically explode.
Besides, with temperatures dropping to extreme lows, rubber becomes brittle.
If this were a flagpole, the temperature facing the sun would be 250 degrees Fahrenheit above zero. In the shadow is 250 degrees below zero. Let's put some rubber on the moon. -90 is the glass transition temperature. It's when the polymer goes from being flexible to a rigid element.
This is what happens when you dip rubber in liquid nitrogen.
So it's extremely cold. Minus
Can't
320
send rubber to the
Celsius.
moon.
This is why almost all the wheels used for exploring other planets have been made of hard metal.
This is actually a spare for the Curiosity rover. It's made out of aluminum, a single billet that gets machined down so you don't have to worry about fasteners or welds or anything like that that could potentially be a failure point.
But with it being so expensive to launch matter into space, the wheels have to be as lightweight as possible.
It's light-ish, but it's still heavy.
To meet those mass limitations, they made this skin 0.7 millimeters thick.
Thinner than a credit card.
Yep. These structural members
Yeah,
here, which
okay.
are also called grousers, they're there to give the wheel strength, but also help grab onto obstacles and help grab the soil. The problem is that
Like
because the
master
rubber is so
that.
large and heavy and the terrain is just so aggressive and nasty, they're actually seeing much higher peak loads kind of focused on areas between these grousers than what was predicted. And this is the actual condition of the wheels on Mars right now. And as you can see, got big holes and cracks where that skin was. Now the wheel still operates, hasn't immobilized the rover, it's still going to complete its
not very
mission,
durable,
but
I
it does
guess.
affect where it can go and how efficient it is.
When you apply a force to a material, that is known as a stress. And what you're really doing is tugging on all the atoms inside the object. And as a result, their spacing changes a little bit, and so the material deforms. For example, if you pull on an object, it will get slightly longer. And the per unit change in length is called strain. Now, for most materials under low stresses, strain is directly proportional to the stress applied. I mean, the more you stress it, the more it stretches. And the material is elastic. If you remove the stress, the object goes back to its original size. So no atoms have moved around and no bonds have been broken or formed. You've just made them flex when you applied that stress. But if the stress applied exceeds the yield strength of the material, well, then the strain is so great that the atoms can't maintain their positions relative to each other. Defects called edge dislocations can move through the material. The atoms are actually rearranging themselves, and so the deformation is not reversible. It's plastic deformation. So the object won't go back to its original shape when the stress is removed. If enough stress is applied, the material can completely fracture. In the worst case scenario, this results in holes like in the Mars rover wheels, which reduce their performance and ultimately could jeopardize the mission. Ordinary metals can withstand a strain of only around 0.3 to 0.8% elastically. Any more than that, and they undergo plastic deformation, so they won't return to their original shape. Ultimately, they could even fracture. Right?
You can go back to the original
Yanked
state
it
again.
and stretched it. And that's why every component of a space vehicle is designed never to stretch more than that 0.3 to 0.8%. But that's a significant limitation. There is a different type of wheel that NASA has tried in space, which are those on the Apollo Lunar Roving Vehicle, or LRV.
That
It's on the
particular
moon.
structure that they built is something that we call a pantograph. All it is it's a set of wires that have been over, under woven.
And this on the surface here to get grip, also to strengthen?
It's primarily to ensure that the tire does not sink into the ground. So they did some studies with these tread strips to figure out how much coverage they needed. And so they found out that roughly 50% was enough to keep the tire kind of floating on the surface and still maintain that flexibility.
The Lunar Roving Vehicle wheels worked well for the short distance journeys traveled on the moon. I mean, the farthest this vehicle ever went was 36 kilometers. But still, these wheels needed to be designed to minimize plastic deformation of the steel mesh.
And so they put this internal structure inside there. We call it a bump stop. So as they hit a bump, and this is deformed, when it hits that, it stops the deformation to keep it just below that proportional limit where they would induce plasticity.
This wheel was good enough for the short Apollo missions, but for longer journeys, a bump
does it
stop
depend
won't be
well
enough
for
to
that?
prevent plastic deformation building up over time. Mesh steel wheels have been tried on Earth, but their performance does degrade over time.
This was the Mars steel spring tire we made and drove on that same test rig, and there's no fracture, but you see a lot of permanent deformation there.
What we need is a material that is strong and durable like steel, but which can endure much more strain without deforming permanently. And that is where this stuff comes in. In
Why is that?
1961, the Naval Ordnance Laboratory was doing experiments with different alloys involving nickel and titanium. A sample that had been repeatedly worked, heated, and cooled was shown to one of the associate technical directors, who just happened to be a pipe smoker. So he decided to see what the sample would do if he applied a bit of heat from his lighter. And when he did that, he found that the material changed shape. This shocked everyone and led to more investigations into the material, which became known as nitinol for its components, nickel and titanium, and for the Naval Ordnance Laboratory, where it was discovered. So why did nitinol change shape?
An alloy.
Well, it's really because the alloy can undergo a phase change in the solid state. In heated nitinol, the atoms are arranged in a cubic lattice arrangement, and this phase is known as austenite. But upon cooling, the atoms ease into a form known as twinned martensite. It's a messier, lower symmetry arrangement of the atoms. And in this phase, you can apply stress to the material and deform it. But unlike in an ordinary metal, this deformation is not causing bonds between atoms to break and edge dislocations moving throughout the material. No, in this case, the crystal structure is changing once again to a D-twinned form of martensite. And now, when you heat it back up, the material goes from martensite back to being austenite, which means all the atoms go back to their original locations, and so the material
that's nice.
returns to its original shape.
We can basically set this shape as the parent known memory shape. That's why we call it shape memory. I can stretch this out. If I cooled it down, I could stretch it out even more. But as soon as I heat it back up, it'll remember that original parent shape.
And that's why
It's
nitinol
nice.
is considered a shape memory alloy. The shape is set at high temperature when the material is in the austenite phase. Then, as the material is cooled down, it undergoes a phase transition into twinned martensite. If stress is now applied to the material in this phase, it can be extensively deformed by changing the crystal structure into D-twinned martensite. When the stress is released, most of that deformation remains. But when the sample is heated, the atoms return to the austenite phase, which returns the material to its original shape.
It's like you're barely in the water.
No,
And it
it's
just,
as fast as you can conduct heat to it or get heat away from it.
Isa kami sa no
whoa.
di kaya lang
that's cool.
titanium.
This is the property of nitinol that most people are aware of, and one that makes it useful for a lot of applications.
So that's a stint.
They slightly cool these down right below to martensite, and then they crush it or elongate it. So you can see it gets real thin. And then they put in a catheter, and that catheter goes through the body to the place where they want to deploy the stent. And then upon deploying it, it bounces right back, increasing that outer diameter and opening that artery. Nitinol is absolutely perfect for that.
Shape memory alloys can actually generate significant forces when they're heated, which means they can also be used as actuators.
You're going to see a huge amount of force and stress build up in the wire, which we can see with here, which how much it's pulling.
6 pounds, 7. You can really see it contracting there. 13, 15, 16, 17, 20 pounds. Oh, it's lifting
Okay.
it.
That's about 90 newtons
It's
of
pretty
force.
strong.
Scientists have even used shape memory alloys to fracture a rock. Shape memory alloys are being investigated for use in aviation. I made a video before about vortex generators, which are these little fins that stick up out of the wing of a plane to trip the airflow into turbulence. This is important for takeoff and landing, to keep the flow attached to the wing so you don't stall.
But when you're up at cruise and you don't need those vortices being generated, you want these to stow because they're a drag penalty. As the plane just climbs from takeoff to cruise, we go from some temperature on the ground to something close to minus 50, minus 60 C at cruise. The alloy is designed in between those so that we can just take advantage of the ambient temperature change that happens in the environment. When we cool this one down, no controller, no operator, it autonomously stows flat.
The temperature at which the material transitions between austenite and martensite can be tuned to be anywhere between minus 150 to positive 350 degrees Celsius. This is done by changing the ratio of the elements and using different heat treatments.
And then as that would heat back up, coming into landing, comes right back up.
And this was a turbulence
This principle has been
in the
extended
airplane.
to operate the main flaps on an aircraft.
Okay.
Now, the heating and cooling is not passive, but controlled by a heating element.
So we've done demonstrations where you have a 737 aircraft and no hydraulic actuators on the wing box. All we have is a shuttle mechanism that's driven by 2 tubes of nitinol, and we've driven those ailerons and flap elements on the wing box of a 737 in flight, 60 degrees flap angle down, 30 degrees flap angle up, just by heating and cooling 2 tubes of nitinol. Replaces all the hydraulics.
The shape memory effect is the main thing people know about materials like nitinol, but they have another unique property which makes them ideal for
What's that?
making durable wheels.
Oh, it's for the
You're just
wheels.
going to take it and you're going to loop it a couple times around your hand like that, and you're just going to pull on that wire and feel 6 to 8% strain in a piece of metal.
Oh, that's really weird.
That's 6 to 8% strain, which you can't do in other wires, right?
But what's
Wait, so how
weird
does it
about it is
feel
that
like?
it feels a little crunchy.
It feel because you're feeling all of the reorientations.
Oh, so weird.
So cool though, right?
Yes, very cool. Can you hear that?
Yeah.
So
How weird
that
is that?
pinging is twinning.
Shape memory alloys can stretch up to 8% of their length and still spring back to their original size. This property is known as superelasticity or pseudo-elasticity, but they're kind of misnomers because the material is not actually operating in its elastic regime. What's actually happening is that this nitinol is in the austenite phase. Its transition temperature is lower than room temperature. But by applying a stress, even with no temperature change, you can force the crystal structure to change from austenite into detwinned martensite. And this rearrangement allows the nitinol to deform by that 8%. And still, it'll snap back to its original configuration once the stress is removed and the atoms return to the austenite phase. That sound you're hearing is the material undergoing a stress-induced phase change in the solid state. If you want to think about it on a stress-strain curve, now this transformation is occurring entirely above the martensite transition temperature. So the material starts off in the austenite phase, and then the applied stress is what induces the phase change from austenite to detwinned martensite. And when that stress is removed, the atoms spring back to the austenite phase, and so the material goes back to its original size and shape.
If this were a normal tube, I would bend it to here and it would plasticize. If it was a brass tube, which has a plastic buckling mode, it would go like this and it would actually buckle the wall. I would never take my hands and bend them like this and have it completely return to shape.
At the bend, the nitinol is transforming from austenite to martensite and back.
When we go from the higher symmetry phase, the austenite, to the lower symmetry daughter phase, which one is it? Exothermic or endothermic?
I feel like that should be exothermic.
Good job, science guy. If you were to put your hand around
I have no
this
idea.
tube, you'll actually feel the heat energy, the enthalpy of that transformation evolving as heat. You ready?
Yep. Oh yeah, that's real hot.
That actually is like burning. Like I can't keep my hand
No,
on it.
keep your hand on it. It won't
Jeez,
burn
that's
you.
hot.
When the stress is removed and the material goes back to being
burning,
austenite,
huh?
that phase change is endothermic. It absorbs heat.
Right? It's like you could use that for a refrigerator.
So it's exactly right. So another area where these materials are being applied is in a field called elastocalorics, where we use this transformation to do things
Like heat
equivalent to heat
Yeah, we
pumping.
could do certain
I
things
want
with
to shoot
that.
this with our thermal camera. We got a FLIR with us. How's that?
This dissipation potential can act a little bit like the dissipation in the shock absorber, right? So the tire itself could actually perform some of that dissipation potential on its own.
It almost acts as a damper
Right.
to get rid of that energy loss. So then your tire actually has the potential of becoming a complete suspension system, which obviously really simplifies building vehicles for space. The original tire, when I put load on it, okay, you can see I'm only transferring a load from the footprint to this little section of the tire, right? By tying this bump stop element to here, when I go through a footprint, you can see now I'm transferring load 360 degrees around the tire, right? By doing that, I have now increased my load carrying capacity significantly without adding any more mass.
So to make a tire out of shape memory alloy, they weave nitinol springs together into a mesh. It's a pretty tedious and time-consuming process.
So you're going to take it like so,
Yep.
I can tell.
both ends,
No.
and now take it.
No, you are
Now
not.
Take it
Yeah.
and screw it in.
Oh my goodness. Are you kidding me? Is this what you do every day?
684 times
684 times
per tire.
But will these wheels work on rovers on the moon and Mars? Well, they test the wheels extensively on
I
a
guess it
rotating
won't then.
carousel of different terrain types, from sand to small rocks to bigger rocks.
So the terrain endurance rig basically consists of a circular carousel
It's
that is
test machine.
independently driven. The wheel tire assembly is also independently driven, so we can create a forced slip condition, so we can drive with zero slip. And this is about how slow a Mars rover would be traveling. Average speed is about 6.7 centimeters per second. That's a nominal speed. They don't go too fast.
All right, I'm gonna go walk on simulated moon regolith. It looks like beach, and it feels like beach. This side is meant to simulate the surface of the moon, and this side is meant to be the surface of Mars. It is very sinky sand. Wheel is rolling along, hits a rock, and am I
This is
pushing
just sink
into
on
it,
the
or
Mars.
do I want to get it on top?
I'd say get on top and just put all your body weight onto it.
That's basically my full weight on it. The shape memory alloy is strong enough to support the weight of the vehicle or vehicle and crew, but it's also incredibly flexible, so it can deform up to 8% without being permanently damaged. And that's what's needed for long space missions.
So that's a pretty good amount of deformation, right?
That's a great amount of deformation.
And still not beyond 8%.
Very squishy.
It's just walking back to the car after the beach. Tricky for a rover, right? But these tires won't just be for space. They're also looking at terrestrial applications.
Most aircraft, the tires on those aircraft, they have to be pressurized to really, really high pressurizations, 300, 400 PSI, not the conventional 30 to 60 PSI you do in a car or truck tire, right? We have issues where at those huge pressurizations, they can explode. The other construct is maintenance,
Explode.
right? So if I'm a pneumatic tire and I'm relying on that pneumatics for the performance of the system, I have to always be checking the air pressure to make sure that I'm at the right inflation pressure so that I'm not burning too much fuel, or I'm not at a place where I could potentially pop a tire because of the loads. By going to a structural system that doesn't rely on air and is designed specifically for the application, all of those things go away.
They've tested one on a Jeep. Since it doesn't rely on pressurized air for support, you just can't get a flat tire. Plus, it can never be
The tire is kinda
underinflated,
weird.
which significantly improves fuel economy. With a metal that works like magic, you can make airless tires that will take us off-road, on-road, into the air, and across other worlds.
How much does that cost though? Very expensive to make and all. It should be competitive with the